Thank you very much for joining our final Liftoff webinar for 2021. Appreciate everyone taking the time to join us today. My name is Joe Steele. I'm the Senior Director of Communications and Legislative Affairs with Lyft. We are happy to welcome EOS today and talk about the shaping of the future of manufacturing. So Kyle Adams will speak with us in just a little bit. But I wanted to go over a few housekeeping items before we get started. You should all be muted. If you're not muted, go ahead and please do so. We are recording this session, and it'll be available on our website at lyft.technology by tomorrow, so you can share it with folks who may have not been able to join today, and you think they might be interested in the content. Please go ahead and share that with them. Also, we will be facilitating a Q&A session after the presentation by Kyle today, so please use the Q&A function that we're all too familiar with these days. Using the Zoom toolbar that should be at the top of your screen, the Q&A button there. Hope everyone is safe and well as we round out 2021, and hopefully 2022 will continue to improve, and we'll get to do more face-to-face meetings. But in the meantime, we are continuing our webinar series virtually here. So again, my name is Joe Steele, Senior Director of Communications, Legislative Affairs with Lyft. I do want to share a little bit of information about Lyft for those who do not know who we are and what we do. Lyft is one of 16 national manufacturing innovation institutes from around the country. And our goal is to drive American manufacturing into the future through technology and talent development. We believe the connection of materials, processes, and systems and talent is smarter manufacturing. And we know at the core of smarter manufacturing is our economic security and resiliency. So the next area, the next region around the world that tackles smarter manufacturing, we're just going to come out ahead. And we as a Department of Defense supported Manufacturing Innovation Institute, we want that to be the USA. So I mentioned, we call that the manufacturing equation, the connection of materials plus processes plus systems plus talent. We know that the combination of that is where we need to be in terms of smarter manufacturing. So we run two programs out of our institute at Lyft, Leading Innovations for Tomorrow, which is our technology program, and Learning Innovations for Tomorrow, which is our talent program. A little bit about Leading Innovations for Tomorrow. It is about, again, materials, processes, systems, everything from the digital side, the integrated computational materials engineering, easier to say ICME, agile and smarter manufacturing, advanced alloy process development, and multi-material joining. I will not quiz you on this slide, but it gives a little bit deeper dive into each of those pillars of technology. So you can see a little bit more of the breadth and depth of where we operate. And it makes sense that EOS is a proud new member of Lyft, and we are proud to have one of their best machines in our facility now that I'm sure Kyle will speak to a little bit later. On the talent side of the equation, Learning Innovations for Tomorrow. Again, it's about innovation, but this time it's about new tools, new pathways, and new venues. And that really begins with our Ignite Mastering Manufacturing curriculum. That is a curriculum where we is a 3-year program for high school students around the country. They are able to take a look at advanced manufacturing, see what manufacturing looks like in the year 2021, from material science to really focus on material science all the way through robotics and smarter manufacturing. We do teach that at our Lyft Learning Lab. Pre-COVID, you see the Learning Lab here. We had students coming to our facility each and every day. There is a online component to it that we have been keeping in touch with our students on throughout this pandemic. So we've kept them going through the pandemic. But this program is rolling out around the country with our partner Amatrol. It is available in 10 states now. So we're very proud of that. So not only are we preparing the students for jobs of tomorrow, we're also preparing students for the jobs of today. And we have a world-class certification program as well as our Operation Next program. So certification programs and Operation Next both tackle CNC machining, welding, industrial technology maintenance. We just launched our robotics program, our robotics technician program here at our Lyft facility in Detroit. So we're very happy to help folks get certified, earn certifications, nationally recognized, industry recognized credentials in those 4 majors. Operation Next, I will highlight as a program for our servicemen and women who 2 ways, both active duty are able to 6 months before they separate from their service, they're able to earn a credential in one of those 4 majors. So by the time they leave the gates, they're able to get a job immediately into industry. That Operation Next is also open to National Guard and Reserve members and their spouses, which is great for those folks who are continuing to serve our country. We want to be able to provide them an opportunity to earn a job in advanced manufacturing as well. So that is available. We launched as a pilot a couple of years ago in 2018 in Fort Campbell, Kentucky. Last month, we announced expansion to Hampton Roads area of Virginia, which is one of the largest maritime areas of the country, a number of military installations there. It's also available to National Guard and Reserve in Michigan, Wisconsin, and Florida. And we're looking forward to continued expansion of the program as we go forward. So as a DoD Institute, we're very proud of that program. Finally, I mentioned that EOS is a proud new member of Lyft. Lyft is a nonprofit 501c3 based here in Detroit, public-private partnership between industry, academia, and government. And we are a membership-based organization. So what do you receive as a member? What are the benefits as a member? Well, we are a trusted advisor. We're hoping to guide people into the smarter manufacturing future, both with our in-house experts as well as the experts around our ecosystem. That includes our friends at EOS, certainly. So we want to help guide people with the best advice we can to help them make a transition to the smarter manufacturing future. We are a technology accelerator. You saw our Leading Innovations program, really taking ideas and concepts from conceptual stage into commercialization, so we can advance those technologies, move them into the hands of the warfighter, and move them into the hands of industry as quickly as possible. A technology showcase, and we do all that work, a lot of that work at our Detroit facility. It is a showcase and a sandbox. We are highlighting the future of manufacturing, the art of the possible, what the future looks like, but we're also in a sandbox. Our technician team is back there each and every day working on projects for members, with the DoD, and again, moving those technologies into commercialization. We're a connector and a convener. Thank you so much for joining today. That is why we are here, to connect and to convene some of the brightest minds in advanced manufacturing around the country, so we can talk about some of the newest and best innovations that are out there. We are a talent developer. We talked about our Ignite program, talked about our skilled trades program, our Operation Next program. Very proud of those. We're developing the next generation of advanced manufacturing. And finally, we are a government partner. We help connect folks with the federal government. It can be bureaucratic. It can be a challenge for folks to make that connection, and we serve as a conduit to do so. So I invite you to follow us, give us a call, visit our website, send us an email with any questions about Lyft or membership. Addie Stone Richards is on the call today. She's available in the Q&A section. She has put her email address in there, so if you have questions, you can reach out to Addie directly. But that is it for Lyft. I know you didn't come here to talk about to hear about us for the whole hour. We wanted to hear from Kyle and EOS. So Kyle, I'm going to stop sharing my screen and hand the presentation over to you. So Kyle, area sales representative from here in Michigan, will talk to us about shaping the future of manufacturing. Kyle, the show is yours.
Thank you so much, Joe. I am going to set up the screen here real quick.
We got you. Awesome.
Great. So thank you very much, Joe, for that introduction. My name is Kyle Adams. As Joe said, I'm the area sales rep for EOS. I'm going to share a little bit about what EOS is, what we offer, and how we can help you with some advanced manufacturing solutions. So we're going to start with a little bit of a company overview, kind of talk about what EOS is, and then move into our machine overview. Who is EOS? So why are we a member of Lyft? EOS, we provide responsible manufacturing solutions in the form of industrial 3D printers. So both in polymers and in metals. We are the world's leading technology supplier. We've been around since 1989. family-owned company, and we provide complete end-to-end solutions. So that means we provide the material, the machine, the process parameters to run those machines, and then also talent to help train you and get you up to speed with those systems as well. As far as our vision moving forward, we have a vision to take key technology and make it for responsible manufacturing, finding the best solutions for future manufacturing and shape the future with our technology. Currently, EOS has over 4,000 systems installed globally. We actually just recently installed our 1,000th system in the United States. Most of those systems being our metal systems, our polymer systems were actually first introduced, but our metal systems have clearly taken off just due to the advantages of advanced manufacturing that we can provide. We have customers in over 68 countries and more than 1,350 worldwide employees. Of that, over 160 of them are based in the United States between service, sales, application, some production, and front office. Moving on from there, some of the solutions and technologies that we provide. First, we're going to talk about our metal systems. This is the type of system that is at Lyft and also one of our highest installed base systems. There are currently 4 systems on the market, or 4 base frames on the market, ranging from the M100, which is a small 100 millimeter diameter circle. Build volume has a 200 watt fiber laser. This is typically installed at universities. It's about the size of a large refrigerator. Very easy to run, doesn't require a lot of accessories. Moving up from that, this system is the system that's installed at Lyft, the M290. This is what we call our workhorse system. It is one of our largest install bases, and it is one of our most mature and developed solutions. It has a 250 millimeter square platform with a 325 millimeter Z axis, and it comes with a single 400 watt fiber laser. This system can run any of our materials. We do all of our development on this. It can run production, it can run prototyping, it can do development, it can do literally anything that you can require out of an additive system, as long as it obviously fits within the bounding boxes of our build volume. One of the new systems that we introduced is the M300-4. So this is, the M300 is a system that if anybody's ever worked with an M290 and they created a wish list of everything they wanted, we took all of those requests and then put them into the M300. It has a larger build platform, 300 by 300 by 400. It has a quad 400 watt lasers installed on it as standard. All 4 of those lasers provide full field coverage. They can work on individual components, or they can all 4 work simultaneously on the same component, completely controlled by the customer. Removable build volumes, gas flow cooling, a lot of things that really take something that, mid-sized platform from an M290 and industrialize it for production long-term. And then as far as part size increase, we introduced the M400 a handful of years ago. So there's the M400 single laser, the M400 quad laser. Both of them can either come with a 400 or 1,000 watt laser, and it's a 400 millimeter cube. This system is probably the most advanced and largest install base large frame production system. Everything else being small and medium frame. The system is extremely robust, great workhorse machine, removable build volumes, and semi-permanent filters, which allow greater runs in between maintenance by the customer. Moving on to our polymer systems, as you can see, there is quite a bit more that we offer, at least it looks that way. We're going to start kind of from the middle here, the P110, the P396. These are our systems that have been in development and in production for an extremely long period of time. They are very, very mature systems, the P100 being a little bit smaller, the P300 being the main workhorse machine as far as polymer material goes. Both of these operate, or all of these machines operate similar to the metal systems, as they're powder bed with a fixed laser and a galvo system. Then we have a large frame system, the P770. This is, as you can see, 700 or sorry, 27.6 inches by 15 inches. Build volume, fairly large, runs 2x lasers. And then the P810 is a high temp version of that machine to run materials like HT23. The P500 is the new production system. This is very similar in lines to the M300 that we talked about previously. This machine is extremely fast. It is designed for production going forward and has integrated modules and removal modules, so this machine can grow as our development changes. Now, jumping back to the left, we also have the P450. This is the first machine that EOS has actually engineered and produced in the United States. So this one is actually made in our Pflugerville office in Texas, engineered there. It is a very modular system. The system was designed with the operator in mind. Parts can be removed, optical benches, everything can be upgraded in the field. So as we grow and as technology advances, this machine can grow with the customer and with our advancing technology. Now, one of the biggest questions I always receive is, what materials can you work with? And the very simple answer is, if you can get it atomized and if it welds, then we can work with it as far as metals go. This is just a kind of a brief overview of the materials that we offer. There is multiple materials within each family, but this is just the main base families. Some of the ones that are of extreme interest are obviously the nickel alloys, titaniums, and some of the, actually for rocket industry, copper. But also as far as medical is concerned, we have cobalt chrome, that titanium again. For tooling, we have the steels and tool steels. And then it is possible, it is doable, it's been proven that it works, but cost of manufacturing is fairly high. Precious metals, gold being one of them, just the cost of material being very, very, very high, but absolutely be able to work with. And then also refractory tungsten carbides, things of that nature as well. And for the polymer systems, these are the 6 main families of the polymer material that we work with. The high temperature PEEK, polystyrene, polypropylene, some thermoplastics, polymer PA12, which is our standard material, PA2200, and then also PA11, which is kind of a more natural version of that. These materials are all developed by our ALM group, which is a material manufacturing group also in Texas. They do a large group of standardized materials, but they also can do custom materials with different things like carbon fill, glass fill, different blends of materials to work with the specific applications that our customers are looking for. Now, how does this process work? How does powder bed differ than other additive processes? Most people know today about the FDM process, where it's essentially a glorified glue gun. The powder bed process, which we operate, is extremely different in it is, we use powder and then we weld it. So this is kind of a cutaway graphic of our M290 system. Its powder dispensing is a little bit different, but in functionality, it is very similar across our entire range of platforms. The way this works is, hold on, let me create a laser pointer to show. We have our main build bed here. We have a build plate that we're working with, and this is for metal. The build plate is a similar material as the material that you're working with, that you're welding. So steel for steel, aluminum for aluminum, tie for tie, so on and so forth. We start with a fresh powder bed here. This is all of our virgin material. This is all material that has not been welded. We use a recoater blade. So this platform moves up. We dose the proper amount of material. So if we're working with a 20 or 40 micron layer, we dose the proper amount of material up. A recoater blade here So we'll travel across the powder bed of what we're working with, this area here, and lay out that 20, 40, or 60 micron layer. This recoater blade can be multiple materials. It can either be a steel or ceramic blade, which is a hard blade. We have options for soft blades like rubber blades. And then also there is a carbon fiber brush blade that we can use as well. So different blades work for different applications. Hard blades work really well for tooling. And most general applications, we work them for very long, very fine and delicate material that we're building. Works very well with the soft blades. Once the powder bed has been laid out, and moved out of the way, we then have the laser come down, and we weld the laser across the part bed. So we're selectively welding the areas that we want at our given layer thickness. Layer thickness works very similar to building with, say, Legos, for a very simple analogy. The smaller the Legos, the smaller the layer thickness, the higher resolution that we can have on the part that we're building with. The larger the layer thickness or the bigger Legos that we work with, the lower the resolution, but the faster you're going to get done. We can work with multiple layer thicknesses or multiple resolutions in the same build. So if you have a large bulk section, we can build that extremely fast and then work down to a very, very thin layer thickness for high resolution detail areas. This process is repeated over and over and over again until we have our final part. That part is then within that powder bed. Everything that the laser has not touched is still soft powder. It can be recycled and reused infinitely. For metals, for polymers, it does have to be reused and recut with virgin material. The part comes out and is ready to go. So this technology has been around since the mid-'80s or so. Technology is ever advancing. We have to keep up on this, just as Lyft's thing, always working on new technology. We are always working on our own new technology. So initially, these machines were intended for prototyping. And in the more recent past, these machines have been introduced for small scale production, high value, low volume components, things like injector nozzles, medical components, things of that nature, where there's extremely high value but extremely low parts per year. Today, with the advent of our newer systems, with more integration of hands-off manufacturing, hands-off processes, we're trying to decrease the value needed and increase that part number per year per part. And these new machines that we're introducing, the P500, the P300s, these are intended for digital factories, our factories of tomorrow, Industry 4.0, whatever we want to call it. They are designed with the intent that in the future, these will be almost completely hands-off systems, and we'll have robots manufacturing most of what we're working with. Now, some of the advantages of additive manufacturing versus, say, traditional manufacturing, and this is really where the industry is at right now, is we're taking that subtractive mindset and trying to convert it into an additive mindset. There's a lot of different aspects that we have to look at, from a very traditional manufacturing point to a more additive standpoint. And there's a big learning curve going on right now. One of them being freedom of design. We have obviously organic structures that are extremely easy for us to work with because we're working single layers at a time. We can decrease the weight of components while also increasing the performance of components using this freedom of design. And typically, we're actually looking at a satellite bracket here. This component here is actually in being manufactured and produced today. This component typically would be one single piece of titanium, but as you look at it here, it is titanium, but obviously extremely lightweight compared to its traditional manufacturing componentry. Functional integration is the next one. So now we're looking at something that may be 5, 10, 15, sometimes even 30 or more individual components being reduced down into a single part. Now, the individual part may have an increased cost. if you're just looking at it at a pure material standpoint, but the decrease in supply chain and manufacturing steps typically reduces the overall part cost, reducing tooling, increasing material efficiency, and increasing or decreasing assembly costs. Next one is customization. So this is very, very important within our medical manufacturers. Being able to take individual components along the production line and have each individual one that's being produced be customized to the end user. Things like knee implants can be individually customized so they're a perfect fit every single time. And then the next one is time to market. A very, very long print on any of these systems, say the longest print we may have might be 14 days. Now, seems like a long time to print one part, but if you are comparing that to, say, a casting or machining operation, this could be significantly shorter to print a component and to work on prototyping and work out bugs than, say, a casting would be. A casting could take 6 to 8 months. Working at the automotive market within my region, they're looking at lead times of 6 to 8 months for one component, where they can get these parts printed within 7 to 10 days. So time to market for a lot of these components and refreshing of iteration design changes moves a lot faster. Now, we offer a wide range of solutions for a lot of different industries. You've heard me talk about aerospace, automotive, we've talked about medical. There is a wide range of areas that we can work within, and we have a lot of experience working within all those different areas. So what we offer, obviously, the solutions, so this is the main thing that we offer, is our system, material, and software. So that is the machine, the material you're going to work with, the process parameters needed to print, and then the software needed to work with all of that. We also have a large team of application engineers, our Additive Minds team. They are specialists in a bunch of different markets, each one being a specialist, so we can work with medical individuals, aerospace, automotive individuals. They have years and years and years of background in each individual area. And then services. So we offer services as far as design iterations, design change, application sprints, a bunch of different areas there. And then, especially in our polymer areas, we also work with some of our other sister companies for post-processing areas. Powder removal, surface finishing, vapor fusing for polymer materials. Our Additive Minds consulting team, which I talked about, like I said, this is over 60 plus employees globally located. They can offer consulting. They can do application sprints, which is taking a particular part from the customer, working through the entire thing from beginning to end with the customer as far as design for AM, orientation, support manufacturing, everything until the final part, and teach the customer how to do each individual step. Also, there is trainings available. We actually have on our website, on EOS, we have over, I believe, 52 individual trainings available for anybody, whether you're a customer or not. You can select individual trainings, or we also have training courses. Those courses include objects such as process engineers, machine operators, and managers. So if you're new to managing an additive manufacturing facility, we can introduce you to training courses so that you can optimize your facility for additive manufacturing, because there is quite a few differences, things like lights out manufacturing that are different than traditional manufacturing. Now, I want to share a couple of our application examples that we have, some of the areas that have been success stories for EOS and for our customers. First one here, this tail bracket. So this part was produced on M400 system, time critical development. So there's cable routing running through this very critical and very complex component. Being able to be produced in one single part was a massive benefit to the customer versus having to integrate multiple individual componentries for a very complex piece. As you can see, 30 components here, reduction from 30 down into 1. And as far as production time, 19 hours to produce this on an additive system versus the traditional manufacturing time of 70 days to produce. So this part made a huge amount of sense. It made massive gains in both time and in performance. 50% less cost, 70 days versus 19 hours. So huge win here. This part being able to be produced on the M400. Injector heads, so this is another part that is extremely complex. 248 individual components reduced down into one individual component, aerospace component. Again, also produced on the EOS M400-4. Again, large 400 millimeter platform, 50% decrease in costs, and significant increase in production time, having to be one individual component versus 240 individual components. So this one here, Automotive Car Accessories. So this is customized individual componentry produced out of Tie 6.4. And being able to produce, so the big benefit here was repeatability of the component without sacrificing quality while also having the increase in customization. So design changes for individual customized components were able to be iterated on just in the design phase. Multiple custom components could be printed on the same platform without having to retool, and all of them being the same quality over and over and over again. And then last design change, so we've worked with Formula SAE teams both in Europe and the United States, being able to produce ultra lightweight componentry for this axle pivot design here. And then also you can see below there is the printed bike. So this is an electric bike. The entire frame being printed out of the EOS M400 system. Increase in rigidity and decrease in weight. Typically with this organic design, we can increase the rigidity of the component going through iterative design and then also reducing weights. Some of our current customers that rely on EOS, automotive market, BMW Group. We have our tier 1 suppliers for aerospace, Centavia, Jabil. We also have sports groups. So sports groups being Under Armour, Bauer. These groups are working with our polymers for protective equipment, for shoes. Obviously, Lyft being one of our new ones. Very, very happy to be joined, be part of Lyft. Original aerospace, so such as Honeywell's, being part of that, and a couple other ones. So these are just the ones we can share, but there are a lot more that really rely on on EOS for their advanced manufacturing needs. So this is something we also offer. This is actually a podcast that we produce. So Fabian Alfeld, he is our Additive Minds consulting manager in the United States. Extremely smart individual. He does, and this is really kind of agnostic to EOS in general, but it's a podcast about additive manufacturing. He interviews people who've been working with additive for an extremely long time, people who have a lot of insight to share with additive, and it's an extremely interesting podcast if you're willing to nerd out on additive manufacturing for an hour or so. Highly recommend it. It can be found anywhere any podcasts are found, but really kind of shares some of the challenges that people go through as far as ramping up with additive, transition from selective or from subtractive to additive, and a bunch of other problems that people have kind of worked with through their AM journey. And I know this is pretty fast, but I'm a fast talker. Went through this pretty quick. Thank you so much for attending, and I hope we have some questions.
Awesome. Thank you very much for the presentation information on EOS and particularly the description of the machine that we have at our facility here in Detroit. We're very happy to have that. Great to explain how it works, why it works, and how it fits into our work in terms of connecting materials, processes, and systems. You can see how we'd use that for prototyping, exploring new materials, and what materials look like when they're completed with that process. That's the whole part of our ICME work is to be able to predict how materials are going to react when they're being processed. So certainly appreciate that. Can you and encourage folks to reach out to Kyle directly, follow EOS North America there, contact Kyle for any additional questions, or you want a deeper explanation to some of those machines and how EOS might be able to help you. And if you have a question, please use the Q&A function here on the Zoom toolbar. Would love to entertain that as we have a few minutes left here to ask some questions. So let's just talk broadly, Kyle, about Additive. You mentioned the consultation services. How often and are people drawn to Additive because it's they view it as the next sexy way to produce products and pieces and components, and if so, I've talked to other people on different webinars on different processing techniques, and how do you go about talking to them through the why, right? I'm assuming that's one of the first questions you guys ask is, why do you want to look at Additive, and does it make sense for them? So can you talk through that a little bit in terms of you're dealing with customers and really explaining the approach to Additive and why it might make sense or not make sense for them?
Yeah, absolutely. It's a really good question, Joe. So in general, there's a lot of different reasons why people go towards Additive. It could be an increase in performance. It could be, there may have a design that just can't be produced any other way. They have a new way of working with things. It could be lead time generation. It could be any sort of reason, and each customer's reason is different of why. It could be just specifically for prototyping. I can't get this molded. I need to make it out of plastic, and I need to get it done, yesterday. Great, Additive system makes sense to them. So we get a lot of different reasons on why they come to us. It's our job to look at those parts, evaluate them with our applications team, and see if Additive makes sense. And to be honest with you, and I'm sure Lyft sees that, there are certain applications that just don't make sense yet, being the caveat. It may make sense in the future. It could be, so one of the biggest questions is, when am I going to be able to buy a car off the lot with an Additive printed part on it? And, it's a very fair question, but even if you're looking at it, a Toyota Camry, say if there's one part on a Toyota Camry, you're still producing 365,000 parts a year. And that's a huge number to produce an Additive. So, are we there yet? No. Will we be there in the future? Absolutely, but it's going to take time. So we're still looking at those more high value components. If we talk about the medical markets, customized implants are the way of the future. Instead of trying to force a kneecap to fit because we have 4 standardized sizes, wouldn't you want the perfect fit every single time? So that is a quality of life improvement, and it's a massive performance improvement for those manufacturers of medical components. So, there's a lot of different reasons. For the aerospace market, it really comes down to performance gains and speed to production. They can get a part printed in even the large parts. So we didn't talk about it here, but there is a system that's based off the M400 that has 1,000 millimeter Z. And it is the end all be all currently for these privatized space manufacturers, because they can print entire rocket engines in one go. Now, if they're getting those casted, they're getting 40% failure rates out of Inconel or titanium. They're getting cracking. They don't have control over that, and they're kind of at the whim of the casting house. So now they bring that production on site. They have full control. It is a little bit slower process than, say, one single shot of a casting, but they have a much higher level of control, and their risk of failure goes down significantly, and their performance increase goes up because now they can work on things like conformal cooling, which is extremely important within the rocket industry and in the hypersonics industry as well.
I'm glad you mentioned, some of the prototyping, and we're not there yet. I mean, that's one of the reasons we exist, is to help advance these technologies, see where they can go in the future. And that's one of the reasons we're happy, obviously, to have EOS on board, and the machine available to us is to help advance it. So maybe not yet becomes sooner, right? So the goal is to make all of this happen a little bit faster. So we have at our facility, we have extrusion presses and forming presses and welding, all kinds of welding equipment and various processes that we're working on all the times, and the M290 is the most recent addition to that. So how do these processes work together with the additive methods that you've been talking about with more traditional manufacturing processes? Do they work hand in hand? It's not a zero-sum game, right? Where one has to overtake the other.
Absolutely. We're not going to put traditional machine tool manufacturer out of business anytime soon. It's another tool to work with. As far as our metal systems, for example, when this material comes out of the machine, it can be welded, it can be machined, it can be worked with, it can move on to the next machine, and it can be joined, it can do whatever it needs to do. So it's not a replacement, it's another tool to work with. It's another arrow in the quiver, as it were, for manufacturers to work with. And it's the same with polymers. You can take this and you can bond it, you can work with it. We don't have a machine that can print an entire bumper of a car, but they can print it in 8 sections and then plastic weld that part together. And now they have a prototype bumper for the next vehicle. So, the material that we're working with, the end product that we produce, works very well with traditional manufacturing. In fact, most of our very successful customers are traditional manufacturing tool shops that integrate additive into their processes.
Awesome. So one of the things you mentioned, and I was interested to hear you talk about, obviously that there's benefits to this method, right? Freedom of design, particularly one of them, and speed of design, right? For developing and printing some of these components. Can you talk a little bit about, and the M290 you mentioned, some of the powder bed printing was the infinite recyclability of the material that's not being welded. Can you talk a little bit about that in terms of additive versus subtractive and the waste savings? Is there an opportunity there to are we saving on materials by printing things this way?
Absolutely. For the metal stuff especially, if you buy 200 kilos of Inconel material, you could conceivably print 190, 180 kilos of material. There's obviously a waste factor because it is a welding process producing soot. We got, a couple areas of loss, but it's percentages, it's single-digit percentages of loss. All the material that's not welded and worked with, we can absolutely take it, reuse it, and run with it. And as far as you're talking about prototyping, let's say traditional prototyping for a bracket. We design it, we get it machined or manufactured, bent, whatever it may be. That material that's not used has to be collected, sent back, and reformed into the raw material that you're working with, whether that's an ingot, sheet steel, whatever it may be. So there's a huge loss there as far as taking it off, taking it back to the original manufacturer and being worked with. With our powder bed process, we literally vacuum all that material up, run it through a sieve screen, and put it right back in the machine and keep working with it. So traditional manufacturing, yeah, we're recycling, especially in metals, they're recycling way more than they ever used to. And, that material doesn't eventually get recycled. But our recycling loop is much smaller. Our recycling loop typically doesn't leave the room that the machine is in, where recycling loop for, say, traditional manufacturing has to be shipped pretty much all around the world. We're sending boats of material to China to get sent into, or get reworked into raw material again. So there is a bit of a difference. Polymer, it's a bit of a different story. We can't forget about polymer. We recycle 50% of everything we use, everything that goes into the system. There's a little bit of loss there, but we are really working very hard for being responsible for some very high reuse materials. And some of our new reuse materials are 80, 90, 100% reuse, which is great for the polymer stuff as well.
That's great. There was a question that came up on you know, if Lyft had a relationship with America Makes, and America Makes is one of the other manufacturing innovation institutes that I mentioned earlier. Also a DoD supported manufacturing innovation institute. I know EOS works with them as well, and their focus has been additive since their inception. But we, as I mentioned, are using the look at additive in your machine in terms of our materials research and our materials studying, especially on the ICME piece. So we're not additive solely as a process. It is a tool, as you mentioned, to continue our research into materials. So I just wanted to answer that for folks who might be tuning in and aware of both and maybe belong to both institutes. But we certainly partner together and work together, and just had all the leadership actually of the Manufacturing Innovation Institutes visit us here in Detroit. So hey, quick question about the end game. I'm curious about this. This is one of my questions. What is the end game relates to additive? Because one of the challenges that I have always heard folks talk about is the speed of completing components, right? Can I mass produce components additively? Is that where we're headed ideally? Obviously, depending on the need, depending on the materials, depending on the process. But you know, you mentioned automotive parts. I mean, the automakers here in town are cranking out vehicles. You also mentioned aerospace, where they're making fewer, obviously. Is the end game goal to try to increase the speed so these can be mass produced, or is it still just dependent on need and system?
Yeah, I mean, it's a really complex question with a lot of different facets.
Sorry about that.
No, it's great. I'll try to answer it as concisely as possible. So the end game is it's not. There's not one specific end game goal for additive manufacturing, especially not for EOS. We are an adaptive system, so the end game for automotive suppliers can be very different than the end game for a rocket manufacturer.
Yeah.
Automotive suppliers are all about speed. We need speed. We need to be 2,000 times faster. That's their end game, and we need to work with that. Now, an aerospace component, yeah, they care about speed, but what they really care about is quality. This part needs to be perfect every single time for us. So that's their end game. They'll take an extra 2 days of production if they know they're not going to fill that part.
Yeah.
And yeah, do they want those 2 days of production? Not really, but if they know they're not going to fail a component and they know that component's going to work and that rocket's going to launch perfectly, then they'll take it and they're going to be happy because that's their end game. So for us, our end game is to make sure everybody can work with this. We want additive, we want our systems to be kind of a household name as far as, like Haas or something like that is just so well known in the manufacturing game. We want to be able to be adaptive. We want to be able to work, with the customer and have the customer's needs met just with our systems. Now, our new systems, the M300, the P500, those systems are designed with mass production in mind. Removable build cylinders, a lot of stuff where the downtime of the system is limited and the speed of production is increased significantly. And there's a lot of other stuff that we're introducing as far as in-process monitoring, which Lyft is actually working with as well, is increasing the quality of those components that are being printed and being able to track the quality of those components that are being printed time in and time out. So there's not one goal in sight. There's many goals and we need to reach them all. And it kind of seems to go in waves as far as what's important and as far as what we're working on. Is it speed? Is it quality? And everybody's working on it. We're all working on it together. But what becomes important, seems to go with the seasons.
No, I got you. I may have worded that question poorly, but I certainly appreciate your answer. And you nailed it in terms of that's why we at Lyft are working with you guys and with your your machine, because we want to make sure that we can show manufacturers how, with our materials research, materials to better predict how those materials are going to react to a given process, how they all can make the perfect part every single time. So it's not just, so, you know, maybe auto manufacturers and every other manufacturer will be able to better predict how their machines are working, how the material is going to react, how it's working on a day in, day out basis. So every part is replicable and perfect every time, no matter the industry, no matter the process. And that's really at the core of our ICME work. So a couple other questions came in. Can you talk a little bit about the characteristic changes of building with iron-based alloys and how you might be able to overcome those challenges?
Yeah, I guess so. In relation to what, but the iron-based alloys, I mean, it is an interesting, you know, there's a lot of challenges there. So there's items like cracking, and I'm by no means a material specialist, so I'm not going to be able to answer this question to the fullest extent. And I do recommend you reach out to me and we can have a further discussion with our material specialist. But there is some challenges to working with iron. You know, we typically work with stainless steel and other things, and there are additives that we can introduce into the material to prevent issues like cracking and some other stuff that may happen when working with iron. But you know, we do have some of those. We actually also have material manufacturers that we're partnered with that are working on those specific special chemistries to be able to work with those materials. In general, the material that comes off a system, and this isn't really answering the question, but just kind of giving a little side thought, is it's better than a casting. It's worse than a forging. It's more like wrought material as far as the material that comes off the system. So there is a little bit different in mechanical properties, and we do need to take that in consideration when we're taking a traditionally manufactured part and working on it with additives. So we have to look at what the actual requirements of the performance of the part and how we need to integrate that into the process that we're working with.
Excellent. Yeah, I mean, I knew that was it might be a tough one, but to answer via webinar might be worth taking offline. You can reach out to us, reach out to Kyle directly, and maybe we could end up working together to answer that question more specifically. So one more question while we still have time is, you mentioned some of the consultation services, and the first question we talked about was, you know, how you work with people that to decide what if additive is right for them and their particular process and their particular components they're making. What steps should a company take to move towards additive as a tool they want to bring in-house?
Yeah, that's first suggestion is, and this might sound a little bit selfish or whatever, is reach out to us. You know, we are the experts in this field. We produce the machines. We have the engineering staff on site. There are a few quote unquote additive consultants that are, you know, independent out there, and you can look those up, and I'm not going to share any of them over the webinar, but they can help you. But realistically, if you want to evaluate additive, we are going to be the first and best step for you to evaluate additive. A lot of what I do is walking in and brand new accounts and looking at what they have and saying, is this going to work? Is this not going to work? We need to evaluate it. And the best thing for us to do, because it's so rapid, is to just try it. You know, we try it, we test it, we see if it works. If it makes sense, we look at the financials of it, the cost per part. There's some really interesting books out there, kind of additive manufacturing for dummies stuff out there. That's not exactly that, but I can find the link and maybe we can send it out afterwards for the actual book. But it's a really great book as far as answering a lot of the really basic questions on should I even get into additive manufacturing, because there's a lot to it, right? And it is such a new field. For manufacturing, you know, it's probably one of the newest forms of manufacturing out there. Right. So it really is, it's really a complex answer, but just reach out to us, reach out to me, reach out to, you know, whoever it may be. I can also, you know, direct you to whoever is in your area, but we're more than happy to look at something, even if it doesn't make sense, because then we know.
No. And I appreciate that. And I lied one more question, and I think it actually might be for for us. Someone wanted to ask about the next step in additive, creating perfect parts. Is alloy development, process refinement, and simulation improvements part of that next step? And I think that might be why we have your machine, and why our materials folks are working on that especially as it relates to simulation, but and the process refinement and alloy development. Can you talk to that a little bit about, is that the next best step for perfect parts?
Yeah. So, I mean, you're obviously working on the material development and the simulation there, which is phenomenal, because, being able to know what material is going to work, what material is not going to work. We obviously showed you a large set of materials, but right now, a lot of what we're doing is, unless it's specific, we're trying to fit applications into those materials. Now, you're looking a little bit differently as what are the new materials that we can work with, which is kind of a new frontier for additive manufacturing. The other part of that is simulation of the process. So that becomes fairly software heavy. First time perfect prints are very rare currently, because we have to, there's a lot of simulation that has to go into a first time perfect print. And we're talking about, web servers and servers on servers on servers of data to crunch those numbers. So one of the things a lot of the software industry is working on is simulation of components for additive. And there is a lot of information, a lot of which you're generating going into this, as far as what's actually happening at the melt pool level of this process for things like stress, warpage, cracking, shrinkage. All of those play key roles into the final component. And the more of that we understand, the better off our first time prints are going to end up being.
Yep.
And it seems kind of crazy, but sometimes we're operating in the, when you watch this stuff print, it's happening so fast that it's very hard, and such a fine level. Our beam spot size for metal, we're looking at 100 microns. Yep. So we're trying to watch something that's 100 microns in diameter, moving at well over 1,000 millimeters a second. And it's just a lot of information to gather very, very fast. So
that is absolutely why we exist, and why we have the M290 in-house, and why we have our experts on staff to look at those materials, study them, understand how they'll react, so we can better predict. With all that data, we can better predict and model it to see what's coming afterwards. I do want to be cognizant of everyone's time. So more questions about specific alloys and other things like that, please reach out to Kyle directly. Appreciate everyone joining today. I do want to thank you for attending today. I want to thank Kyle for his presentation. Thank you to EOS for their membership and partnership. We look forward to all the things we can do together going forward. And that concludes our 2021 Liftoff webinar series. I invite you to join us as we kick off again next year in January. In the meantime, please follow us, reach out to us or Kyle with any questions specifically. Sign up for our newsletter and our email notifications so you can learn about our upcoming webinars. Again, this will be posted on our Lyft.technology website. And thank you, everyone. Thank you, Kyle. Thanks for joining today. Hope everyone has a great end of the year and a great holiday season. And we'll talk to you next year.
Thank you, everybody. Thanks, Joe.
Thanks, everyone.